An ideal vapor compression refrigeration system uses R134A as its working fluid. The system operates between 8 bar and 1 bar. The compressor inlet is superheated by 10 degrees Kelvin, and the condenser exit is subcooled by 5 degrees Kelvin. The refrigerant flow rate is 0.1 kilograms per second. Determine the refrigeration effect and the coefficient of performance. So the first thing to do here is realize we're working with a vapor compression refrigeration system. So the best way to summarize our given information is to draw the components that make up that system and put the properties that we've been given at the proper place. So a vapor compression refrigeration system consists of 4 components. So the first component I'm going to show is the compressor. So that'll be the compressor. The discharge of the compressor goes into a condenser. So we go out of the compressor, up into the condenser. We'll show the direction the refrigerant is flowing here. So this is our condenser. Then out of the condenser, we go into a throttling valve. And then out of the throttling valve, into the evaporator. And then out of the evaporator back into the compressor. So just show the direction of the refrigerant flow right there. Number of the state points around here, doesn't matter really where you start, but we'll start at the inlet to the compressor as 1, 2, 3, and 4. So that's what a vapor compression refrigeration system looks like. So now we'll go back and read through the problem again and put properties at the right place on here. An ideal. So the first thing we see here is it's an ideal vapor compression refrigeration system. Well, remember what that means is that the isentropic efficiency of the compressor is 100%. That's what ideal means. It's using R134A, so we'll just note that the working substance here is R134A. So that tells us which of the tables we're going to have to get information from. The system operates between 8 bar and 1 bar. So this is where you need to know something about how these things work. The high pressure, 8 bar, is going to be the pressure up in the condenser. That's the high pressure. And the pressure down in the evaporator is 1 bar. So the compressor is getting us from 1 bar up to 8 bar. And then the pressure drops down through the throttling valve from 8 bar back to 1. Both the condenser and the evaporator are heat exchangers, and so they operate at constant pressure. The compressor inlet is superheated by 10 Kelvin. So we have to read that carefully. This is not saying that the temperature at the compressor inlet is 10 degrees Kelvin. It's saying the refrigerant is superheated by 10 degrees Kelvin. So what that's telling us is that T1 is equal to the saturation temperature at 1 bar plus 10 Kelvin. So it's superheated by 10 Kelvin. So it's 10 Kelvin higher than the saturation. And this also says the condenser exit is subcooled by 5 Kelvin. So same idea there. It's not telling us T3, but it's saying T3 is the saturation temperature at 8 bar this time, minus 5 Kelvin. Okay, so very important to know what that phrase superheated by and subcooled by means. Other thing it gives here is the refrigerant flow rate. So the mass flow rate of the refrigerant is 0.1 kilograms per second. And what we're asked to find is the refrigeration effect and the coefficient of performance. So we'll list those next. Find refrigeration effect. So we need to know what refrigeration effect is. The refrigeration effect is the cooling rate that the evaporator produces. So it's the heat transfer into the evaporator. And it's a rate of heat transfer. Refrigeration effect is always a rate of heat transfer. So refrigeration effect is Q dot evaporator. And B, we're looking for the coefficient of performance. Beta is the symbol we use for that. So next we list assumptions. Or at least we start a list of assumptions, and we will add items to that as we progress through the analysis. So the first thing we're asked here is the refrigeration effect. So let's go just back and take a look at our diagram and see if we can figure out some of the properties. See, where do we know properties? Well, we know the pressure here and we know the temperature, so we can certainly fix the state at point 1. That's no problem. And notice up here, this point, the condenser exit, we also know the pressure and the temperature there. So point 1 and point 3 we can fix the state. So that's all good. Problem we have right now is point 2 and point 4 we can't fix the state. However, if you take a look at the very first thing we were asked for was a heat transfer into the evaporator. That state is fixed. Right now this one isn't, but remember that through a throttling valve the enthalpy is constant. So if we can go to this point and get the enthalpy, then we can, that enthalpy is the same here. So it looks like we should be able to get this heat transfer rate into the evaporator. So because that's the first thing we're asked for, Q dot evaporator, that's the first thing we're going to go after. Now, any of these problems where we have multiple components like this, we're always going to end up applying the energy equation multiple times. So what I suggest we do here is right off the bat start with our most general energy equation and make all of the assumptions that we can make for every component and simplify it down to one that we can then apply to each component. So starting with our general energy equation. Rate of change of energy in the control volume with respect to time is heat transfer rate minus work rate plus summation over the inlets of mass flow rate, enthalpy, kinetic energy, and potential energy, minus summation over the exits, m dot exit, h exit, v exit, plus g z exit. So what assumptions can we make that apply to every component no matter what? Well, there are a few of them. Steady state, so make the assumption here, steady state, and cross a term off. Kinetic and potential energy is negligible, so Ke and Pe negligible. We can make that for every component, so that gets rid of all of those terms. So now we have an equation that's that we can apply to any component we want, and all it's going to be is heat transfer, work transfer, and the change in enthalpy across that component. Notice any individual component we look at is going to have just a single inlet and a single exit for this system at least. So we're going to start off by looking at the evaporator, because first thing we want is a refrigeration effect, and that's Q dot in the evaporator. So when we apply this equation to the evaporator, we can make an additional assumption that there's no work transfer in the evaporator. Okay? So work is going to be equal to 0 for this particular component, and there's just simply no shaft sticking out of the evaporator. So Q dot for the evaporator is going to be equal to the mass flow rate times H at the exit of the evaporator, which is 1, minus H at the inlet, which is 4. So H1 minus H4. So that's the simplified form of the energy equation for the evaporator. So H1 we can get because we know pressure and temperature there. We'll do that in a moment. H4, we'll have to look at the throttling valve to get that. So let's get our H1 first. Well, at P1 equal 1 bar, first thing we do is look up the saturation temperature. So we go to our tables for R134 and we look up the saturation temperature and we find it's minus 26.43 degrees C. So that means that T1, remember T1 is saturation temperature plus 10 degrees C. In other words, the refrigerant is superheated by 10 degrees C there. So T1 is minus 16.43 degrees C. So those are our two properties, pressure and temperature, and of course we know we're in the superheated region. So we go to the superheated table for R134A and we find this gives us an H1 of 239.45 kilojoules per kilogram. Never a bad idea while we're in the table anyway getting enthalpy to get the entropy as well. And turns out we're going to need that. So that's 0.971481. It's not the end of the world if you don't look up the entropy right away. Later on when you find out you need it, you can go and get it then. But I'll just write it down there. So we know the enthalpy at 1. So the first part of this refrigeration effect calculation at least is done. But H4, we have to sort of temporarily look at the throttling valve. So for the throttling valve, if we take a look at our energy equation so far, in the throttling valve there's no heat transfer and there's no work. Okay, so we're assuming that there's no heat transfer in this throttling valve, so we should say here that it's an adiabatic throttling valve, which is a very good assumption. They are not very big things. There's not a lot of surface area for heat transfer, so there's not going to be any heat transfer in the throttling valve, and there's certainly no work transfer. I mean, there isn't even a shaft coming out of it, so that's no problem. So what's left of the energy equation? Those two terms are gone. The mass flow rate in equals mass flow rate out. We can cancel that out. It just tells us that H3 in this case equals H4. So that's what the energy equation tells us for the throttling valve. Well, the reason that's important to us is we're looking for H4 in order to complete this calculation. So that means we can figure out what H4 is by looking at point 3. And point 3, we know some properties there. P3 is 8 bar. So just as we did in point 1, we need to first of all look up the saturation temperature, and it turns out that at 8 bar the saturation temperature is 31.33 degrees C, and therefore, because it's subcooled by 5 degrees, the temperature at 3 is 26.33 degrees C. So we have a subcooled liquid coming out of the condenser, subcooled by 5 degrees. So now what we actually need is the enthalpy. And so using this temperature, we can get an enthalpy at point 3, and that works out to 86.222 kilojoules per kilogram. And of course that's also equal to H4. Now the way we found this, of course, remember this is now a liquid. So once it's a liquid, we can ignore this pressure, and this H is just the saturated liquid value at this temperature. So that's where this comes. It's the saturated liquid enthalpy at that temperature. Okay, so that's where we get that. So now we can return to our evaporator, and we have all of the numbers we need for Q dot evaporator. So Q dot in the evaporator is equal to the mass flow rate, 0.1 kilograms per second, multiplied by H1, 239.45, minus H4, 86.222, and both of those are kilojoules per kilogram. So this works out to 15.323 kilowatts. Okay, or Q dot evaporator, which is the refrigeration effect, is 15.3 kilowatts. So that's our first part of this. Next, we're looking for the coefficient of performance. So remembering what the coefficient of performance is, it's the refrigeration effect that we just found, Q dot evaporator, divided by the compressor work, or more correctly, the absolute value of the compressor work. So this part we've got. Now we need to turn our attention to the compressor work. So let's go back and take a look at that. The inlet conditions we know. We already used those for the evaporator. We also know this compressor has an isentropic efficiency of 100%. And we know the discharge pressure is at 8 bar. So this is pretty standard calculation of this compressor. We're going to have to figure out an extra property at the exit, but because it is isentropic, that's the entropy. So we can take the entropy at 1, it will be the same at 2. So then we have our two properties at the exit, entropy and pressure. So we can get exit enthalpy. So that's what we're going to do. So we start working with the compressor. And again, we have to assume that the compressor is adiabatic, right? So we need to make that extra assumption. So we have an adiabatic compressor. And so the work rate of the compressor is equal to mass flow rate, H1 minus H2. And again, mass flow rate we know and H1 we know. So 0.2 is all we need to know. Well, to get 0.2, remember that the compressor is isentropic, so S1 equals S2, which we looked up already when we looked up the enthalpy originally for 0.1, so that's 0.971481 kilojoules per kilogram degree Kelvin. And also, P2 is 8 bar. So there's our two properties, 8 bar and that entropy, and this will put us in the superheated region. The inlet to the compressor is slightly superheated, so as it goes through the compressor it'll actually move out further into the superheated region. So we know this is going to be superheated, so we go to the superheated table for our 134A and we find H2 is 284.51 kilojoules per kilogram. So we can complete our work calculation for the compressor. Mass flow rate, 0.1 kilograms per second. H1, 239.45 minus H2, 284.51. Both kilojoules per kilogram. So the work of the compressor is minus 4.506 kilowatts. So we can get our coefficient of performance because we have Q dot evaporator and work of the compressor. So coefficient of the performance is 15.323 divided by 4.506. Remember, it's the absolute value of the work, so I drop that negative there. And this is 3.4002. So we conclude that beta is 3.40 is the coefficient of performance.